Hello, for the people connected in the Zoom meeting remotely, can you hear me well or not?
Yes.
Okay, yes. Can see Jalal, that's okay, thanks. Perfect.
So, good morning, everybody. So, I have the honor to chair the committee for the PhD events of Luca SANTOSUOSSO. Excuse me for the pronunciation. And this PhD thesis is about distributed stochastic optimization for operating complex virtual power plants, leveraging cascaded run-of-the-river hydropower flexibility for renewable energy integration. So I will first introduce the jury. So we had two reviewers, so referees. So Gianfranco Chico from Politecno di Torino is online. Lennart Schroeder, excuse me also for the pronunciation, professor at KTH Royal Institute of Technology, and also online. And Acer Thomas Gart, professor at Norwegian University of Science and Technology from NTU. There are also two other people, a member of the jury. So Jalal Kanzempour, professor at Technical University of Denmark. Malcolm McCullough, professor at University of Oxford. And myself, research director at INRIA in Lille. And the two supervisors of the PhD thesis are George Karianatakis, senior researcher at Mines Paris PSL, and Simon Kamal, junior researcher at Mines Paris PSL. So we will start with the presentation of your work. Okay, so you will have So we'll have 45 minutes. You will have 45 minutes to present your work, and then we will ask you some questions. So just before we start, if we have troubles with the network, so they can send you a message. If somebody online has trouble with the network, he sent you a message. Okay. Okay. So the floor is yours.
Thanks. Merci, Madame la Présidente, pour cette introduction, et merci à tous pour être ici aujourd'hui. I will continue on the presentation in English, also because, as you can listen, my French pronunciation is terrible. So let's start, as I have a lot of slides to show you. There is the outline of the presentation. So I will start with some context, and then we will go into the details of the methods proposed, conclusions, and perspectives. So the central concept of this thesis is the VPP paradigm, the virtual power plant paradigm, which here is defined as an aggregation of heterogeneous, geographically dispersed energy resources operated as a single entity to participate in the electricity markets and provide ancillary services to the grid operator. Actually, what I want you to focus on is that the VPP here is not only the aggregation, the portfolio of resources that we operate, but also how we operate them. So the intelligence that is behind this aggregation. It's actually a paradigm that emerged in the 1997 as firstly called as a virtual utility. So it has my same age. Today, there are various definitions of virtual power plants that coexist. So there might be a bit of overlap with other related concepts like aggregators, power producers, or energy communities. That's why I wanted to point out our definition, which comes, of course, from a summary of the state of the art in the literature. So why are we interested into virtual power plants? Well, a VPP can be used to exploit flexibility sources like storage systems, which can be aggregated into the VPP portfolio of different sizes from small scale to large scale units in order to mitigate the stochasticity of renewables or processes in which the VPP is involved. It can also facilitate market participation, especially of small scale units, for example, most of distributed energy resources, and also can benefit from smoothing effects derived from aggregating variable renewable energy sources. as well as enabling a coordinated and smart operation of this portfolio of units across multiple electricity markets. What we are interested, the main focus, let's say, of this presentation is the concept of flexibility and how can we exploit virtual power plants for flexibility, where we provide or we take better a definition of flexibility based on what you see here. So the capability of a power producer or consumer to modify its production or consumption level in response to an activation signal, in particular in our case to mitigate the stochasticity of renewables. So how can we operate a virtual power plant? Well, what is the intelligence behind the VPP? So typically, 3 different functionalities are involved in the energy management strategies of a VPP: forecasting, scheduling, and dispatch. The forecasting stage predicts random variables involved in the VPP operations. Scheduling optimizes the allocation of the energy resources in the market to maximize the objectives, typically economic objectives of the VPP. And then a dispatch phase at a lower level, which controls in near to real time or short term phase the assets operation to minimize the cost of deviations from the scheduling from the schedule of the VPP. So our focus is on the scheduling and dispatch phases. In particular, we will propose methods to address these two functionalities of the VPP. By facing key challenges involved in this process, which can be summarized as managing uncertainty and handling the complexity of the problem deriving from non-convex dynamics involved in the VPP, as well as coupling constraints and multiple stages involved in the energy management. We take the perspective of a real-world aggregator, the industrial partner of this PhD, which is Compagnie Nationale du Rhône, which is actually a French power producer and concessionaire of the Rhône River, as well as an aggregator of third-party energy resources. To give you some figures, it's quite an important player here in France, with 25% of France's hydroelectricity production. And it operates as main assets a cascade of 19 run-of-the-river hydropower plants here in the south of France, which is the core of their VPP. Currently, the virtual power plant of CNR is managed in 2 distinct groups. So they have a tool for operating the renewables, so wind and solar units, and different tools for operating cascaded hydropower plant, so independently. At both stages, they employ deterministic tools, optimization and control tools, predictive control, for example, at the lower stage, with also non-economic objectives involved. The main question that was initially motivating this study is the one that you see here in the bottom part of the slide. What if cascaded hydropower, wind, and solar units were jointly operated in a stochastic economic framework? So investigate a transition from an independent operation to joint operation, while transitioning from deterministic to stochastic management of these portfolio assets. What is actually done in the state of the art is briefly summarized here in relation to the main objectives and the challenges of this thesis. So first of all, in terms of modeling, there is quite lack of general models for VPP operations in terms of physical dynamics, but most importantly, a generic modeling for decoupling within the VPP, between the assets, the physical assets and components of the VPP, which we will address. Scheduling and dispatch phases are typically addressed independently rather than in a more realistic energy management tool as a comprehensive approach, integrating both scheduling and dispatch, both phases. As for centralized strategies, when deterministic models are employed, like in the case of CNR, of course, there is a limited ability to hedge against the uncertainty, which motivates a transition to stochastic models. And on the other hand, in general, for centralized approaches, especially scenario-based stochastic models, there is typically they might exhibit poor scalability as well as limited adaptability and privacy and other properties. If we look at alternatives to centralized approaches, so non-centralized optimization and control methods, what we have identified is that two main challenges arise. So on one hand, the composition methods are typically restricted to a single dimension. I will go more in the details of this later on in the presentation, but in few words, they typically address only a set of coupling constraints, for example, the temporal coupling or the coupling within scenarios in the VPP, which of course limits the scalability of the resulting distributed methods or the composition methods more generally. And they typically lack of performance guarantees for non-convex problems. So unreliable methods when we go to complex aggregations. So the overarching objective of this thesis is to develop a generic, comprehensive, and stochastic decision-making framework for virtual power plants participating in the electricity markets, while ensuring scalability and the reliable operation of the VPP. So let's move on to the first part, where we will discuss modeling, scheduling, and dispatch of virtual power plants, proposed methods for decision-making. So the objective here, as we were saying, is to develop a generic, comprehensive, and stochastic decision-making framework, addressing in a sequential manner these two phases involved in the VPP operations, scheduling and dispatch. You can see here the same scheme that we were discussing a few slides before, with a specific focus on these two functionalities. What we propose is a scenario-based stochastic programming for the scheduling phase, 24 hours before injection, and scenario-based stochastic economic model predictive control, MPC, for the dispatch phase. In particular, we focus on providing a generic formulation of the scheduling problem, which in turns, when participating, for example, in the day-ahead market as the main case studies here, it involves, let's say, optimizing these two terms, energy cost and penalty due to imbalances, subject to coupling constraints and individual constraints. And the objective here is to give a generic formulation of these coupling constraints to abstract a little bit the formulation of the optimization model. So focusing on coupling constraints, they actually, let's say, the main reason for focusing on these constraints is that these constraints are the sets of dynamics, if you want. They describe the dynamics that the VPP has to address in a centrally, so in a central manner, because they connect all the assets and components of the VPP problem. That's why we want to abstract their formulation and separate them from the individual dynamics of each asset to get a generic model. So the types of coupling constraints considered here are the electrical coupling, for example, the power balance within the VPP, physical coupling, the fact that, for example, the state of a given asset N might depend on the control action at the level of another asset N prime, temporal coupling, so the dynamic evolution in time of the state space model describing the physical behavior of a given asset, for example, a storage system, as well as scenario coupling, typically fixing here and now decisions in a two-stage stochastic problem. So as you can see, we have basically two types of coupling constraints, physics-related constraints, or something that depends on the physical dynamic of the assets involved, and model-related coupling constraints, or something that depends on the way we model the optimization problem, in this case, the uncertainty within the stochastic tools that we employ. And focusing on scenario coupling, depending on the bidding approach that is employed, we have two different sets of coupling constraints that we were formulating here. For example, if you look at the at the left-hand side of the slide, when we employ fixed hourly bids, so fixing the quantity that is offered in the market for all level of prices, we will have a specific set of coupling constraints, while with price quantity bidding curves, the quantity varies as let's say with the price level. So we will have couples of energy offers and price levels, which will create the price quantity bidding curves and the different bids submitted to the market. And in the dependently on which one of these bidding strategy we select, we will have different set of coupling constraints, as I was saying. So constraints that enforce fixed energy offers in the fixed hourly bid case, or constraints that enforce non-decreasing price quantity bidding curves when we go with bidding curves, and they will create a scenario coupling within the optimization model. As for the proposed dispatch, what we propose is a scenario-based stochastic economic MPC, which basically mix concept of scenario-based stochastic programming with economic control. So the scheme, in the scheme that you see here, basically the optimizer receives the bidding curves computed at the scheduling level, as well as the forecast, intraday forecast on the random variables involved in the control process, and then computes the control actions to be submitted to the energy resources in a loop following the standard MPC approach. Specifically, we call it stochastic economic MPC because it combines concept of stochastic programming and economic objectives. So you see that basically we have prices involved in the objective function, as well as scenarios to model the uncertainty, for example, in the prices of the VPP. And we compare it with benchmark methods involving deterministic economic control and reference tracking control. So the standard reference tracking MPC, where we minimize the difference with respect to a given reference, or the deterministic version of the stochastic MPC, where prices are considered explicitly in the objective of the controller, but in a deterministic manner. So let's move to the case study. As I said, we take the perspective of CNR of this company, where we assume that the VPP participates in the day-ahead market subject to a number of coupling constraints and individual constraints. In particular, we consider 4 sources of uncertainty involved in the problem: inflow, water inflow into the hydropower assets, solar and wind power, as well as market prices. And the problem, we can sketch the problem as in this slide here. So basically, we have we optimize the market profit of the VPP, which means fixing the decisions within the controllable assets of the virtual power plant, which are the hydropower plants in the VPP. So turbines discharge and barrage discharge across the hydropower systems. Subject to the electrical coupling, the first coupling constraint, hydraulic coupling, so water outflow plus the external inflow from the Rhone River gives the inflow into the downstream asset, in a very simplified way, of course. Scenario coupling, when we consider scenarios, individual dynamics of each asset, which in this case are non-convex dynamics, because the hydropower generation function is a bilinear function, and we propose a McCormick approximation of this bilinear term, as well as operational curves, which are employed specifically by CNR to control its assets. I will try to explain this briefly. So they relate on the x-axis the water inflow with the water level of the reservoir, and depending on the water inflow, the flexibility potential, the flexibility capacity better than of the hydropower system. So the storage capacity of the hydropower system varies as a function of the inflow, and we will have a storage capacity to exploit only during a specific range of inflow in the so-called energetic periods, while during low flow periods and flood periods, we have practically no storage capacity. That's why we call them run-of-the-river hydropower plants, even though we have, I mean, in a specific range of inflow, a small storage capacity to exploit. So moving to the results of the application of the proposed decision-making tools to this case study. First of all, an out-of-sample validation was performed to assess the number of scenarios needed to actually represent the uncertainty in the scenario optimization and control scenario-based stochastic optimization and control problems. I won't go into the details, but the sketch of the procedure is given here. So first we solve the scheduling optimization considering only a set of training scenarios. We fix the first stage decisions and we recompute the second stage decisions using testing scenarios. We evaluate the testing objective and we take the objective function error as difference between testing and training objective function values. In this case, considering 2,000 testing scenarios, we find out that 20 scenarios can adequately capture the uncertainty in this kind of problem. So as a main reference, we will consider 20 scenarios to solve both the linear and mixed integer version of these models. As for the simulation setup, we consider 12 run-of-the-river hydropower plants in a cascaded system combined with wind and solar units, as you see in the figure, within a simulation period that ranges from 3 months to 1 year using data from 2017. For the scheduling and dispatch phases, we consider 24 hours horizon and 6 hours predictions horizon respectively, hourly optimization for the scheduling, and updates every 10 minutes from the dispatch at the control level. And all the results that I will show you come from an ex post evaluation, so after the uncertainty is realized. If you remember, the initial question was, what if cascade hydropower, wind, and solar units were jointly operated in a stochastic framework? So we try to address this question with the results that I'm showing you. As for the jointly operation, we were able to prove that jointly operation of hydropower and wind and solar in the CNR case leads to a profit increase on average of 2% compared to independent operation of these units. Specifically, the economic value of the aggregation depends on the river inflow conditions. You can see that depending on the specific period, we have a different increase with the coordinated approach compared to uncoordinated operation, because we have different inflow conditions. So for example, in March, where we have a very low increase in the profit, it's because we are in a flood period. And if you remember the previous operational curve, the storage capacity depends on the specific inflow conditions that we are able to observe and partially control through the cascade. We also evaluate the sensitivity to wind penetration in the VPP. So you can see here the normalized VPP profit on the y-axis and wind penetration on the x-axis. And the results here is that when we increase the penetration of wind into the virtual power plant, the profit per megawatt hour of VPP capacity reduces, which means that the flexibility capacity provided by the cascaded hydropower system is progressively consumed as the penetration of wind increases in the virtual power plant. So it is not unlimited, the flexibility that we have. We will have to find a good balance between renewables and storage capacity. As for the stochastic economic framework, economic control increases by 19% the profit of the VPP compared to non-economic traditional reference tracking control, so model predictive control without an explicit formulation of the key performance indicators in the problem. Why? Because with our stochastic economic MPC, we are able to control not only the discharge of the hydropower plants and shift them to during the peak price periods, where it's more convenient, of course, to produce energy, but also the hydropower flexibility, which means the storage capacity of the hydropower plant can be controlled through the cascaded system to have enough flexibility capacity to maximize over peak price periods when convenient. So we do not only control the power generation, but also the flexibility available at in a given period using the hydropower plants in the cascaded system. As for the stochastic control, we find out that it improves by 24% the profit of the VPP compared to deterministic non-economic control. So you have an increase with deterministic economic control, but even a higher increase when you put also a scenario-based representation of the uncertainty. And finally, we investigated how price quantity bidding curves compare to fixed bids, dependently on the bidding strategy that we select. And in particular, we get quite a relevant increase when using price quantity bidding curves compared to fixed bids. Even though when using too many scenarios to represent the market prices, and so too many breaking points in the bidding curve that we build through the scheduling stage, we might overfit to the representation of the uncertainty. To give you an example, here you see 4 different price quantity bidding curves for 4 different sets of scenarios, 5, 10, 15, or 20 scenarios. And the interest in using these bidding curves, specifically with an adequate number of scenarios, is that we can increase the breaking points in the bidding curve, and so exploit additional flexibility to solve our bidding problem, let's say. So to summarize this first section, the motivation was to assess the benefit of the combined operation of cascaded hydropower and renewables within a stochastic framework. The main contributions are the generic formulation of the coupling constraints and dynamics within the VPP optimization model, as well as the comprehensive 2-level stochastic economic decision-making framework for VPP scheduling and dispatch. And as main results, we show that run-of-the-river hydropower can be effectively used to mitigate the stochasticity of renewables, as well as the benefits of stochastic economic control compared to non-economic and deterministic control approaches. Now, a new challenge arises, let's say, when you transition to a stochastic framework. So scalability, which is often associated with the BPP management when large-scale portfolios of assets are involved, is not, let's say, limited only to large-scale portfolics. For example, when we have a complex VPP, so complex a VPP with complex internal and external dynamics, which means physical internal dynamics, but also interaction with the external actors like the market. In the case of complex virtual power plants, we might encounter scalability problems even with medium-scale portfolios, not very large-scale number of large-scale portfolios involved in the problem. And this is the case of CNR actually. Because of the non-convex feasible space of the problem, the hydropower coupling, the uncertainty involved in the problem, which increases the complexity significantly. And so the new question that we were trying to answer at this point was how can we can we develop a VPP decision-making tool that keeps scalability while ensuring reliable operation of the VPP. And this is the second part of this presentation, where we present distributed VPP optimization and control tools. First of all, let's go through the alternatives to centralized optimization. So we have many different schemes that can be implemented. Actually, here we consider these 4 different approaches. So centralized optimization, which is the classical one, where a central controller gets all the information from the assets and computes and solves the energy management. Decentralized methods, where local controllers control the local assets without any interaction. Hierarchical methods, which distribute the intelligence among central controller and the local controllers, and distributed methods with local controllers that exchange information to reach convergence to the global optimum of the problem, the original global optimum of the problem. And in particular, each one of these schemes has its own specific properties. We are interested into optimality and scalability specifically in this work. And the reason for investigating distributed optimization is and control is that we can balance the optimality and scalability of the control tools compared to alternative approaches like decentralized and centralized methods. So first of all, we have to reformulate the VPP decision-making problem in order to enable its decomposition. The main limitation, again, is that existing decomposition methods are typically restricted to only one set of coupling constraints or only one dimension of the problem if you want. For example, methods tailored for a special decomposition of the electrical and coupling constraints, or alternative methods which are typically used for decomposition of the scenario coupling constraints. Here, what we propose is a combined scenario spatial decomposition for the scheduling phase that can be combined with model predictive control to scale also in the temporal dimension of the problem. So this is the original centralized optimization problem of CNR. The structure that you see on the right-hand side of the slide is the proposed decomposition problem, where the electrical coupling, where we have basically 2 types of sub-problems, one which accounts for the power balancing within the VPP, and another set of sub-problems which accounts for the individual dynamics of the hydropower assets in the problem, and they are linked through the coupling constraints, electrical, physical, and scenario coupling that we discussed in the previous slides. While the individual constraints and the objective are allocated to the specific subproblem. So each local hydropower scheduling subproblem accounts for the individual constraints of each hydropower plants, while the power balancing subproblem coordinates, let's say, if you want, the operation. How can we actually implement this decomposition? We reformulate the problem as a consensus problem, where the global variables involved in the coupling constraints are first identified from the electrical coupling and the physical coupling. So you have that hydropower generation and the discharge for the turbines and barrage are the global variables involved in the 2 coupling constraints that we want to decompose. We duplicate these variables and we allocate them to the local problems, and then we enforce consensus constraints with the associated dual variables for consistency. The results is that we, from a complex mill problem, we get n times omega small mixed integer linear problems plus 1 large linear problem, where n is the number of hydropower plants and omega is the number of scenarios. So a decomposed structure, which in general is much easier to solve because these sub-problems can be solved, of course, in parallel with the proposed distributed and scheduling and dispatch methods. So as for the distributed scheduling, the decomposed problem is solved using the ADMM, the popular ADMM method. I won't go into the details, but the 3 main steps are highlighted here. So local primal variable update, global primal variable update, and dual variables update, and while enforcing a sharing of the information between local agents to enforce convergence. Here you see, for example, a very simple example of application of the ADM method to a simple linear problem. We first perform the so-called Lagrangian relaxation, and then we solve the relax problem through these 3 steps that are in the slide. Why are you I am showing you this? Because there is actually a limitation of the ADM method that we want to address. So these 3 steps, again called the local, global, primal variables update and dual variable update, they cannot be performed in parallel in classical ADMM. Why? Because we need to solve the second sub-problem, the local primal variables update, the value of the primal variable at the current iteration. So here, classical ADMM is just a hierarchical method, not fully distributed. And that's why we are trying to find something more scalable to address the dispatch phase, which is actually, which needs to work near to real time in short term. So the distributed dispatch is not using ADMM like in the scheduling phase, but an alternative approach which combines model predictive control, stochastic MPC with the auxiliary problem principle. And the difference with respect to ADMM is that we take mathematical steps, an augmented term, the linearization of the augmented term in the Lagrangian, plus the addition of a quadratic separable term to get sub-problems that can be solved now in parallel. And when we put together the APP method, the auxiliary problem principle, with the stochastic economic MPC, we get our distributed stochastic predictive controller. So to summarize, again, scheduling and dispatch solved through two different distributed methods, an application of ADMM for the scheduling and combination of auxiliary problem principle plus model predictive control at the dispatch phase. This works very smoothly for convex problems, as we will see in the results, but not too much for non-convex problems. And that's why we investigated the reliable distributed methods. So ways for having trustworthy methods that we can rely on. So the main limitation of both ADMM and APP that are implemented in the dispatch and the scheduling phases is that they cannot guarantee performance in general for non-convex problems. The proposed solution was to enforce upper and lower bounds on the distributed solution derived through consensus ADMM. You see a scheme here, let's say, of the proposed algorithm. So basically, if the distributed solution is the one that you see in black, we have no guarantees that this distributed solution will converge for non-convex problems. The optimal objective function value, the true optimum, is in green, but of course you will not know this during the iterations of the algorithm. What we propose in what we call consensus ADMM with bounds is to derive from the distributed solution at each iteration upper and lower bounds, and we can take the difference between the upper and lower bounds as a sort of optimality gap to evaluate the optimality of the proposed distributed method at each iteration, as well as proving with a novel proof that the validity and existence of these bounds for mixed integer problems, so to get a guarantee of reliability of these methods compared to the state-of-the-art approaches. So let's go to the results. First of all, distributed predictive control. So when we implement our distributed stochastic APP at the dispatch level, we get an average execution time which is reduced by 10% compared to centralized control with more than 99% of accuracy. Remember that this works only for the convex model. And we were also able to investigate the impact of tuning in the parameters. So the fact that these augmented Lagrangian relaxation-based methods, they are typically very sensitive to poor tuning of the tolerance parameters, penalty parameters involved. As for scalability and reliability, which were the main questions of this section. So even for the mixed integer problem, so for the non-convex model, the proposed cascaded ADMM with bound reduces runtime by 57% compared to centralized solutions, and by 35% compared to classical ADMM. And in terms of reliability, we get practically no failures, so almost 100% accuracy compared to centralized methods and existing ADMM, where the failures explode as the number of scenarios increases in the optimization problem, in the scheduling problem. Here you can see some examples of behaviors of classical ADMM in comparison to the proposed methods. You can see that typically they exhibit this oscillatory behavior, and again quite large sensitivity to the tuning of the parameters involved. While with our approach, the proposed consensus ADMM with bounds, we are able to regularize the convergence of the algorithm. It also reduces significantly the number of iterations required to converge from more than 1,000 to 200 iterations. In the full case study, so when considering 20 scenarios, what we find out is that classical ADMM, it completely, let's say, it does not converge at all. So it's, as we were saying, completely an heuristic methods for non-convex problems. While with the proposed methods, not only we are able to converge even in less than 600 iterations, but we also provide through the use of these upper and lower bounds a measure of the optimality gap, which can be used by the operator to assess the reliability of the method. Here, just to give you an example of how the distributed method can actually coordinate the PPP operations with our proposed method. You can see 3 different periods: energetic, low flow, and flood periods of the inflow within the hydropower cascade. What the figure is showing is that when you see a drop in the observed value of renewable power generation, whenever storage is available, so whenever flexibility capacity of the hydropower cascade is available, for example, during the energetic period, the distributed approach is able to coordinate all assets to react to this drop by consuming flexibility to compensate for the drop in the renewable power generation. While of course, when we are in periods in which we have no flexibility, this cannot be done even by the decentralized approach. Just to give you an insight on how the operation of the hydropower cascade works. So to summarize, the main motivation was to ensure scalability of complex VPP optimization and control problems without impacting reliability. Main contributions are stated here. So a fast distributed predictive controller for the dispatch phase based on the APP method, a full-scale decoupling of all the coupling constraints involved in the VPP optimization problem, and a trustworthy ADMM-based distributed approach for optimization and control with a performance guarantee even for mixed integer problems. And the highlights of this section are stated here. So distributed MPC reduces execution time by 10% compared to centralized control. And our cascaded ADMM with bounds outperforms both centralized methods and classical ADMM in terms of scalability, as well as achieving very high accuracy with the proven theoretical guarantees, so mathematical proof that which is given in the manuscript and in the paper that you see here. So let's move to the conclusions and perspectives. So some key messages from this presentation are, first of all, rather than isolating VPP scheduling and dispatch as independent phases, we should think about them as a comprehensive sequential functionalities within the same decision-making tool to let's say, reflect the realistic operation of virtual power plants. Through the use of stochastic and economic model predictive control, we can improve significantly the dispatch and also the profit of the virtual power plant in market-oriented problems. With a generic formulation of the VPP can be achieved only when only focusing at the coupling constraints, so the actual constraints and dynamics that relate the different assets within the VPP, as well as the different components in the VPP optimization model. Scalability and decomposition can be achieved by exploiting the generic formulation of the coupling constraints to derive a full-scale decomposition of the problem, as we show, and the reliability of the distributed algorithms can be guaranteed with mathematical proofs even in the even for non-convex models of the virtual power plant. Some perspectives. So, broader evaluation, all what I've presented here is tailored to the CNR case study, so it will be very, it will significantly enhance the value of these results if exploring additional case studies, complex virtual power plants and other market environments, as well as considering multi-market trading and larger portfolios, including additional flexibility sources like storage systems. Exploring alternatives to the proposed methods, so alternatives to stochastic programming to hedge against, for example, worst case scenarios rather than the average value of the uncertainty of the, let's say, prediction of the uncertainty, alternatives to distributed optimization and model predictive control using AI tools to enhance scalability, for example, reinforcement learning, which is particularly suitable to the application of, to be applied to these kind of problems, or online control methods that can enhance the scalability of the dispatch phase as they do not require forecast to be solved. And also addressing additional challenges which we do not face here, like robustness to communication failures and the possibility to introduce asynchronous communication within the distributed approach, or validating the applicability of the proposed distributed method to ensure, for example, privacy through in the exchange among sub-problems of the decomposed structure. So, just to conclude, a list of publications which were the main outcomes of this PhD, as well as a number of conference publications and presentations that I gave in the past 3 years. Some acknowledgements of institutions which were involved in this PhD and projects in which I had the honor to take part. And that's it. Thank you very much for your attention, and yeah, I'm open to answer your question, of course.
Oh, thank you very much for this presentation, just on time. So we will start with the questions, and we start the questions of Professor Ager Thomas-Gard, my neighbor.
Thank you, and I'd like to start with congratulating you with a very nice thesis, which covers a lot of interesting aspects, both from a power engineering perspective, energy systems perspective, and an optimization perspective. So of course, that means also that it opens for more difficult questions when you have such an advanced and nice thesis. So sorry for that, but I'll try not to be too hard on that. But I like to start with the conceptual framework. If you look at your underlying assumption, if I get it correctly, you assume that the agents in these markets are price takers, so they don't affect price. And very often you read in the literature, and in particular a bit simplified literature, that if you have perfect competition, every agent could bid into the market its marginal cost curve, and each supplier, each customer could bid its demand curve, and you would get the central planner solution would reflect that kind of behavior. And you take as a starting point that this is not the case by looking at BPPs, where you get a benefit from coordination, and you showed the benefit from coordination indeed in your paper. So what's the reason that these VPP solutions benefit so much from coordination?
So yes, as for let's say as for the dimensionality of the VPP, anyway, maybe you recall it. I don't need to get the slide. So the idea here is to face let's say VPP with complex dynamics, so not with large scale portfolios like in the case of CNR. Because of this, and because also of the size of the French market that we consider here in this case study, we assume, as you say, that the VPP is a price taker. So this is, let's say, the underlying assumption and perspective of CNR. In this case, even as a price taker, due to the flexibility that we have within the VPP of the CNR, the benefit in having a coordinated approach is to exploit the flexibility that we get from hydropower. So even if you cannot really rely on a very large portfolio of assets, the fact that you can rely on even limited but available flexibility can gives you the benefit from coordinated operation rather than uncoordinated approaches.
But let's say that you have a hydropower plant and a wind power plant to simplify the system. So why is there a benefit from coordination and not bidding the wind power plant into the market alone and the hydropower plant into the market alone?
Wind and hydro?
Yes.
Well, the benefit is from this as well. I was saying, from using the flexibility of hydropower to compensate the stochasticity of wind. We'll get one slide on this. For example, this one. Of course, given that you have let's say an intelligence within the VPP that can actually recognize this and exploit it to coordinate the operation. So for example, in the case of CNR, you see that we have this storage capacity that can be exploited. Given that they are participating in the same market, in this case, the day-ahead market, the balancing perimeter of the price taker, in this case, of the aggregator which is operating in the market, is given by wind, for example, or renewables plus the hydropower systems. When, for example, we see an unforeseen drop of renewables compared to the original schedule that was initially submitted to the market in terms of price quantity bidding curves, and if we have, let's say, storage capacity that can be exploited, through the coordination, we can, let's say, discharge to compensate this drop, so exploit the flexibility potential of the hydropower plant to mitigate the unforeseen drop of renewables in such a way that we will in turn minimize the penalties that the cost of penalties incurred by in the day-ahead market in this case study, or let's say in any other kind of market-based procurement of energy that you might think of. This is an assumption that we take dual pricing scheme for the penalty of prices. So in this sense, but let's say the core idea is independently of the way in which you price the imbalances. In my opinion, the core idea is that you will exploit this flexibility potential to compensate for errors in the scheduling phase at a lower level.
Sorry, but we don't hear the questions in the internet.
Maybe you can use the other one. Yes.
Okay, so the question is related to the benefits of using a VPP as compared to bidding into the markets alone for each of the individual assets. So I think if you look at cascaded hydropower plants, there is one obvious observation that differs from that gives a benefit, in my opinion, from bidding in a coordinated way, and that would be the cascaded plants. So one decision that is made by one plant affects the decisions of the other plants. There's one benefit, but I want to stress a little bit this: if you have one single wind power plant, and it's of course stochastic behavior, and you have the hydropower plants, and so why would me as an asset owner benefit from not just bidding the wind power plant into the market by some rule and the hydropower plant into the market by some rule?
Same market, so let's say...
Yeah, let's say day ahead, just to simplify it, or whatever market there is with a clearing date and a balancing cost.
Well, in the end, for me, let's say, depends, of course, on the type of hydropower plant that you would consider. Let's say it's not purely run of the river, so you can enforce some sort of controllability on the asset, so you can control it in a strategic way, which is partially the case of CNR, even if you take individual assets. Then the benefit is like if you're aggregating a generic storage systems with wind. So the fact that you can benefit from the available storage to compensate the stochasticity of wind.
Yeah, but these are difficult questions, I know, and also I'm not completely sure of the answers myself, so it's a good discussion. But let's say that I recognize that there is an asymmetric balancing cost. So, for example, overshooting has a different cost than undershooting in my wind power plant. So I put up a stochastic model. You could use a newsboy type of model, and you could compensate for that in your bid. So you don't bid the expectation, but you compensate for that. And then I optimize my hydropower plant in addition, and I bid in the best possible way to utilize the asymmetric imbalance costs from my hydropower plant. So is there a benefit then in terms of coordinating the two?
Well, the specific, let's say, strategy that you will use to operate them, of course, it will depend, for example, on the prices that you will observe in the market. So this is a variable that will impact the specific strategy. What I want to say is not that, let's say, in every case you have a benefit from the coordinated operation, let's say, but if you want in a reverse way, you cannot do worse than uncoordinated with a coordinated operation. This is why I think that the coordinated operation is beneficial to be investigated.
And then this is of course true because you show in your papers and in your work that there is a benefit. So for me, I like to try to understand where this comes from. One observation I made over the years is when you add also stochasticity into this and you look at the portfolio aspects, it would be possible to offer firm services, for example, into a flexibility market. So you could offer from a portfolio perspective, you reduce the total risk.
If you go to a scenario with multi-market trading, let's say, where, for example, hydropower plants in many contexts, they are also involved in the provision of flexibility, it might be more beneficial, let's say, to operate the assets independently in two separate markets, for example, hydropower for selling flexibility or and renewables in the day-ahead market, then operating them jointly in the same market, like day-ahead. This might be the case, even though we have not tested this in the...
Or even jointly in multiple markets, because you
or even,
portfolio effect out of that. So what could be interesting to look at is in some way the two values, the value of aggregation. So what do you benefit from aggregation, and the value of flexibility? So in some way, based on your very nice research, this could be one interesting thing to look at. So where does the value come from? Does it come from addressing flexibility, or does it come from aggregation, or from both?
Let's say in our specific case, accordingly to the results that what we have, it's really the flexibility which is driving the reason for aggregating or not. So for example, if you look at periods where we have no flexibility, like during floods, because we cannot control the hydropower plant, there is actually very low benefit in going with a coordinated approach, because we have no flexibility to exploit. But there are also other, let's say, things involved. For example, a smoothing effect that you might have when putting together geographically distributed resources, and this will lower the error statistically, depending on how these are distributed geographically.
Good. Interesting discussion. I think also nice research could be done in this area. So I want to move on to your bidding curves. So if I remember correctly, there are mostly staircase curves in terms of you have one scenario with one price and you calculate the optimal volume for that scenario, and you provide a staircase bidding curve. And I think one of your last slides, you also showed that with more scenarios, you get also less steps in your staircase than the number of scenarios. So one other approach could be to say, let's define some price points for the curve independent of the scenarios. So let's say you have 200 scenarios, but you decide on 10 price points instead, and then you use those 10 price points as a starting point for creating price curves. How would you approach that? Would that work?
How would you select the price points, randomly or without some sort of...
From insights, I would say. So you would guess from observations more or less where the price curves will be, and then you could say, I want to find optimal bid volumes for those price points.
Let's say that what we do here, first of all, is that we take scenarios in a random way. From the given set of scenarios, we select randomly a subset of these scenarios to build these price quantity bidding curves. If you select the scenarios in an intelligent way, which for example can be done by scenario reduction methods, even for other sources of uncertainty, then you might get the same performance in terms of profit, even with a lower number of points, because you don't need probably the whole set of scenarios to represent accurately the uncertainty in the market. It's not something that we have tested, but I mean, my intuition is that you might get the same performance even with a lower number of points. But this really depends on how you select the scenarios, in my opinion.
So how important is it that it is staircase curve, this one? So in another approach, if you choose, let's say, looking at your curve, there are maybe 5-6 price points will be okay, and you could increase to as many scenarios as you like. But instead of doing this staircase, you could say that any scenario where the price is given, you would do a convex combination of 2 points on that curve. So you could approximate from those 10 points. You would in principle get a piecewise linear bid curve.
Yeah, that is quite a good alternative approach, I would say.
It depends on how important for you it is to have the steps, or if it's even better to have an increasing price curve piecewise linear.
Well, let's say the only reason for having this comes from the way in which the market's constraints is modeled. So the fact that you need to enforce that the price quantity bidding curves are non-decreasing, of course, otherwise exactly. It doesn't make sense.
Same in both approaches, I would
say.
Yeah.
But I mean, if you comply with that kind of constraints, I guess that also, I mean, alternative shapes can be employed.
It's just an idea to follow up. We have some papers nice. Where we use that approach, and obviously that gives another dimension to it, where you can do convex combination of 2 points and fit any point on
Yeah, in a way, it's like, let's say, having an additional flexibility to shape the curve as you want to maximize the profit. But it is done in 2 steps or not? In like first this and then a convex.
Yeah, so typically in the first stage, then you decide on with the given price points that you have, you decide on the volumes for those price points, and in the second stage, you will find a convex combination of 2 of those price points in any scenario given on the price in that scenario. In that way, you could have 100,000 scenarios and 10 price points, and you would.
Makes sense.
Basically,
yes. Very nice. Actually, I will have a look. Thanks for pointing this out.
And then if you go to chapter 4 and the algorithmic approach, it's very, very nice work. By the way, I like both results and your way of thinking on that. Myself coming from stochastic programming, of course, there are many similarities between the ADMM method and what we call the progressive hedging method in scenario aggregation, which is also augmented Lagrangian style method. Can you say something about
it's exactly that. What we call consensus ADMM is progressive hedging. They are the same method. The step forward in the, let's say, compared to progressive hedging is this mathematical proof that we give to enforce the bounds on the reliable method. But what we use as a main strategy, underlying strategy, is progressive hedging.
Yeah. So if I understand the paper correctly, you do this in a symmetric way, so that everything is coordinated exactly. You collect the consensus from each of the sub-problems at every stage. So there are some interesting developments, among others, I think, with some of the authors you have in this paper that look at asymmetric coordination schemes for the dual variables.
I think that can be also beneficial in terms of addressing communication failures. So combining it like with asynchronous communication, that can be, it was actually something that I had in mind as a next step in this in this kind of research. But yeah, I haven't done explicit simulations on that, but I guess it's something that can, I mean, improve significantly the algorithm in terms of scalability, for example.
It seems more or less like your problem is inviting for this kind of asynchronous approaches. So it would be very interesting to see if it could easily be adapted to that. My guess is that it could.
I think yes, actually, I was looking at a couple of publications a few months ago on that, because again, I was thinking of about it as a next step. So I think it could be easily applied, actually.
Interesting. I think I should round off, but I have also one question related to your model predictive control and your dispatch stage. So I assume the reason you're using model predictive control is that this is sort of a multi-stage stochastic information process where you get uncertainty resolved and you make decisions.
Yeah, exactly.
In many, many stages. So what kind of assumptions do you have to make to get this to work? Is it Markov assumptions or?
In terms of, let's say, properties of the controller?
Yes.
So the difficulty is that when you put inside MPC economic objectives and constraints, the classical, let's say, proofs of controllability, convergence, all the control properties of the MPC, they cannot be, let's say, extended easily from reference tracking MPC in terms of, let's say, these properties. In the first paper that I mentioned, so the one specifically on stochastic economic MPC, we provide analysis of this based on the Lyapunov functions to demonstrate their convergence actually over the time for a specific class of economic problems, which are formulated as shown in the slide, so to optimize the market. But it's not something that is inherent from MPC theory, so you will have to extend the proof actually to do it.
So if you compare that again to a stochastic programming approach, you would probably assume some Markov properties and do an SDDP type of.
If you, the proof that I mentioned was for the deterministic case, the one with the Lyapunov function. So if you extend to a stochastic case, I guess you will have to go with the Markov process of the.
But if you look at your stochastic economic MPC, it seems to work quite well, and that is a bit impressive. So how would you compare that to a typical STDP approach with Markov assumptions?
Let's say it's not really the same thing in the sense that with SDP you decompose the two stages involved in the problem. Okay, while with MPC you look at the let's say prediction horizon, in our case 6 hours, and you continuously update the iterations for each time steps by switching the window in which you look into the future. So it's not the benefit that you get is not only by decoupling the phases, but also by this rolling horizon approach, which gives you like a limited view in the future that you can set as a parameter. So I wouldn't see these as really as alternatives approaches. You can also implement them together. So have an MPC and then decomposing using benders, for example, if you have multiple stages involved.
Yeah. So it will be interesting to discuss further, maybe over lunch or.
Yeah.
So
Thanks.
Thank you.
Thank you very much.
No, thank you very much. So we go for another group of questions. So questions asked by Lennart Schroeder. So you are online. Can you hear us?
Yes. Can you hear me?
Thank you. Yeah, perfect. Thank you.
Okay, problem for me was then that I was going to ask a lot of the questions that we got from the previous questioner. But I will start with this with VPP. Is this really, you call this a virtual power plant, but it's really this the type of power plant that you are called virtual power plant? Isn't this just a traditional power producer scheduling?
So first of all, let's say the idea here is to have methods that can be generalized to a generic VPP, in which you might have both power production and consumption. That's why we focus on this idea of flexibility, because you need to have dispatchable and non-dispatchable units, so something that gives you flexibility, and you will be able to extend this with the coupling constraints and the generic formulation also to other cases, in my opinion. As for the case of CNR, they have, let's say, the traditional role of power producers, but they also aggregate a third party owner units, for example, wind and solar power plants within the same portfolio and the same balancing parameters. And then they will solve the bidding problem, as you said, with the, let's say, role of only producing energy, not consuming it, but as an aggregator, let's say.
Because what I know about both EU legislation and all other challenges is that what you have today, a challenge for example, an aggregator. I know one in Sweden, and they are, for example, controlling batteries that are in citizens' homes. And these batteries are then also fueled or charged by the user from the retailer. And then there is a discussion that if you're an aggregator of a resource that is inside the retailer's business, then you should have also some kind of contract with the retailer. And that is one of the, as I understand, the fundamental challenge with both VPP and aggregators, that they are also, I mean, they are not the sole controller of the equipment. I just some comment about that. Have you studied this? Because there you really come into VPP, where you are, I mean, you have several actors that are in reality controlling a certain source or are impacted by a certain source. Any contact? Because that has to do with this type of method that you have here can be also transferred to other kind of applications.
Yeah, well, what I can say on that is that if you go really at the level, for me at least, as I said initially, I mean, there is, from what I've seen, no really like standard definitions of virtual power plants still now. You might also have, let's say, alternative aggregations like technical virtual power plants, which are not even used for market purposes from what I've seen, for example, in the US. When you speak about, let's say, in, I guess, very small scale units like at the level of smart homes or for the retail markets or stuff like that, for me, it seems more like an energy communities or something that is very localized and aggregated also and operated as let's say a joint portfolio of assets, but very localized in a specific location, rather than aggregating units that might be geographically sparse in a very large, let's say, environment, which is the main thing differentiating virtual power plants with energy communities, in my view of this. So it's maybe is the fact that this is a portfolio which is sparse, might cover, for example, the whole country, like in the case of CNR, where they have units in the north, in the south, and this gives additional benefits compared to localized energy communities, for example, in terms of smoothing effect.
Okay, and then to more the same area as a little more discussion around this with why you should coordinate or why you should not coordinate. Assume that you have a central controller of all the power plants and flexibility in France, and then they will decide how to operate these specific hydropower plants that you have. And that is what you should have, a market that result in that you should have perfect price signals. So this hydropower plants that you are studying are operated in an optimal way. Assume that you then have these, you can call it decentralized, where you have a specific company that is operating this one. Does it then matter how much wind power they are controlling? Should they change their operation depending on how much wind power they are including in their portfolio? Do you mean that?
Let's say it's not really the number of wind units that are integrated, rather than the forecast error that you have. So the stochasticity that you have within the VPP, which typically goes with the number of units or renewable capacity in the VPP. But if you assume that the process is not stochastic, that you could see actually the power generation in advance, of course, there is no benefit in using any source of flexibility.
But reality is, of course, that I mean, I don't question in any way that you are using stochastic optimization. That is, of course, in some way you have to do that if it's robust or stochastic or something. But the question is this coordination with the wind. Let's say that this company is purchasing or operating twice as much or 3 times more wind power from the same, I mean, taking it from other ones in France. Does that mean that they should then operate their hydro in a different way?
Depends on the units. For example, on how they are placed geographically, because of these smoothing effects. So if they are all in the same location, probably they will have the same pattern. If they are sparse in France, they will probably have slightly different patterns, which when they sum up, they will lower as a smoothing effect, the variability of renewables. So it depends a bit on the setting of the VPP. If my intuition, we tested this only for the case study of CNR, so with their let's say geographical distribution of assets. If you have a large number of wind units located more or less in the same area, which will sum up in terms of variability, then you will have to let's say, increase in a proportional way your flexibility potential to compensate this, my intuition.
Okay, but then from my point of view, I think that if you get different operation depending on who is owning what, then I think there is a problem in the market, since what we also heard a previous person asking about is that if you have perfect information and you have perfect pricing, then you should you should not coordinate. But then I have a linked question to that. In the systems you are studying, it was hard to find the details, but are there any physical coupling between, for example, the hydro system and the solar and the wind? Are they in some kind of areas where you have, let's say, transmission problems, so you cannot run the wind at the maximum at the same time as hydro or something? Are there any physical couplings between them?
No, there is no coupling between hydro, wind, and solar. So and actually CNR is not involved in the process of managing grid operations and reliability. So like not even providing grid services or things like that. Okay. There is a coupling among variable renewable energy sources, so wind units which have or solar units which have the same point of common coupling with the upstream grid. But from our point of view, when we assume that we have no controllability on these assets and we do not have to take into account congestion management or grid reliability, doesn't make a difference from the optimization model point of view. You can just sum up all the renewable.
Okay. Well, as I understand, at least in your basic setup, your hydropower units are not selling balancing services to the system. Is that correct?
Exactly, yes.
Okay,
he's not participating in the provision of ancillary services. Of course, they will have to account for their own balance within the balancing perimeter.
So okay, because I think that is the reason why you in reality get a benefit of coordination with the wind, because you don't have an extra income where you are providing services for the system value. When in your you can call it base case, and that of course and that means that the wind has to pay for these services, but the hydro cannot benefit it from it. And that is, of course, I think that is the reason why you get a benefit from the coordination, that they are not participating in this ancillary service market.
Are you thinking about a scenario in which, for example, we bid wind and solar in the day-ahead market and hydro in the balancing market in a completely independent way? Because if this is the case, I think, as I said before, that you might get an increase when these two sets of units, they participate independently in two separate markets.
Because I mean, let's say that the wind you are balancing is going in, let's say, more wind than less wind than expected, but the wind in the rest of the country is getting slightly less than expected. This means, of course, that from the system point of view and from pricing point of view, you should probably use your hydropower in order for the system balancing and not for your local balancing. And you should probably earn more money on that, because that is what you are seeing in the prices.
Yeah, exactly. What let's say to clarify this, I'm not saying that operating these assets in a coordinated way is beneficial in any possible scenarios. So you might have scenarios in which, because of prices, because of let's say a specific demand or production level that you might see, you don't really get much of a benefit. What I'm saying, what is the message, is that for me, at least accordingly to these simulations, when they participate to the same market as in a coordinated way, you cannot do worse than uncoordinated. So it cannot be worse to go coordinated rather than uncoordinated. But it might be the same thing. I mean, you might not get any benefit.
Okay, then there was something that I didn't find so much details about. Perhaps I've missed it, and that was about for your scenarios, what did you have scenarios for? It was for the up-regulation and down-regulation prices, and then you had for wind, and then you had for hydro. Sorry, it was for wind and for solar, and then you have different scenarios for what's the outcome. But did you have any correlation between these setups?
This is quite a sensitive point, actually. So accordingly to, let's say, as I said, I was trying to find the slide with the scenarios. So maybe this one here. So yeah, we have 4 different sources of uncertainty involved: water inflow into the cascade, solar and wind power, as well as market prices. Let's say these scenarios are not computed directly by me or by us. These are inputs from the company. What I can say is this is ensemble forecast for inflow, solar and wind. And accordingly to previous thesis that is also cited in the manuscript, they were showing that inflow, wind plus solar and prices, they show very low correlations accordingly to the let's say the way in which they have these assets displaced in.
But what is not really clear to me, first of all, for inflow, if you see day ahead, does that really have a big impact? Because that is not what we have seen in Sweden, that they are uncertain for tomorrow. Or are these important? I mean, solar and wind, they can of course be rather different compared to what you see, but can really inflow for what you know now for tomorrow be very uncertain?
Not really. I mean, in terms of error is of course much lower than wind and solar.
Exactly.
We recompute it at both levels, so day ahead and short term. But yeah, it's impacting much less than wind and solar, of course.
But then about the price, what I ask for is a bit the up regulation and down regulation prices, because of course if it's more windy than expected, then you will get more need of down regulation than you get need for up regulation. So I think that that's just what I think, but perhaps you have studied it earlier, because price, I think, what is price here? Is it the up regulation or down regulation price, or is it because you have an extra? I mean, normally you have a certain price for tomorrow, but then of course you also have this the change price for the imbalance pricing. Because the imbalance pricing, I think, has to do with if you are getting more wind or less solar or something like this. But I don't know.
Consider that the penetration of wind and solar in the French market is very low as for now. So I don't think it will directly impact. I mean, I'm sure it will not directly impact this in a clear way. It's mostly nuclear power here that plays a role.
Right. Okay, then just I didn't see so much details about the hydro. Perhaps that is a secret in the company, but have you considered, for example, the flow time between the rivers? How did you feel consider the, let's say, the end time? Is it a fixed price for storing water at the end of the period, or how did you all these details? I assume that yes.
Yeah, let's say in terms of water propagation time, we model it based on the observations of the company as constant time, which you need to propagate from the upstream asset to the downstream asset. Apart from that, the modeling is basically what I show you. So these coupling constraints within the hydropower cascade and these operational curves that are used to model the agricultural constraints and other safety constraints which the company has to account for at the level of each hydropower asset. So you will have a different operational curve for each hydropower plant.
Okay, thank you. That's all from me.
Thank you very much.
Thank you very much. So just we consider now the questions of third reviewer. So Gianfranco Chico from Politecnico di Torino. So Gianfranco, can you hear us?
Yes, yes, perfectly.
Thank you.
Okay.
So please go ahead.
Okay, if the candidate wants 1 minute to breathe, so it's not a problem. Otherwise, we go.
Is it okay for you?
Yes,
Can
yes,
you...
yes,
okay.
yes. Sure.
Okay, okay. So, well, first of all, I have to say that I really enjoyed the reading of thesis. It's a
Thanks.
very interesting structure, very interesting and elegant formulation. So this is what we are expecting from a PhD thesis, but it's not always given for granted. But congratulations for the arrangement. I have to. I have a few questions that are not going in the details that you have already discussed with the previous rapporteurs. One thing is flexibility. You have flexibility in your title. And you also used one of the definitions that are classically given, but you have an interesting terminology here in one of the pages, the flexibility potential of the aggregated system, which is a very interesting concept. My question is, do you have a formulation for that? I mean, this is, as is written, flexibility potential of the aggregated system is something that could be associated to a mathematical formulation because to a measuring unit, to something. Can you comment about this, just to leave it not only generic, but giving a practical meaning to that?
Yeah, let's say in terms of flexibility potential, at least in the case studies that I consider in the thesis, they are basic storage capacity that we can exploit. So you can quantify them in terms of say megawatts or let's say storage capacity which is available. Of course, here, which is quite an interesting point. In the cascaded system, the flexibility potential that you have depends on the way in which you operate the assets. So you, at least for this specific case study, you cannot really give a closed form let's say representation or equation, for example, to evaluate the flexibility potential, because it will depend on the way you operate them. So on the scheduling and dispatch phases, on the optimization and control algorithm, the amount of flexibility that you will see at each specific time. The way why I'm speaking about flexibility, let's say potential in the thesis, is that if you look at a given period, in the given period, the inflow will remain constant because you cannot create water, it will be that. So the capacity, the storage capacity over this given period is the same. But the way in which you use it, each time step within the period, it will depend on the optimization. So you cannot evaluate them at each time instant of the period. Is it clear or not?
It's clear, it's clear. I'm just inviting you to think about that because when we talk about flexibility, generally, we first create the feasibility limits, and then we go and see which is the operating point, and then we see which is the margin, also depending on the time, of course, on the changing conditions and the ramp rates and everything you can have. So probably it's not impossible to define something more structured with this concept, but I find it
yeah,
very
absolutely.
interesting.
Maybe in a more conservative way, like a set that can be conservative in the sense that it depends then on how you operate that. But yeah, that's true. Actually, it's quite a good insight on that because you can actually formulate it as this.
Okay, let's change focus. You have used the term sampling, and just to be sure, normally when we talk about sampling in general, I mean not in your application, But sampling is used as a term for taking many points, many samples. So this is more signal processing. And sometimes is also used, even if it's not so often used like this, is also used to take one sample, I mean a short-term input, for example, once each 15 minutes, but the sample is taken from 1 minute only. So you are not monitoring continuously, you are taking samples each quarter of an hour, but the sample has a duration of, limited duration of, for example, 1 minute. So you are not covering the whole range. On the other side, I am typically thinking about averaging in the sense when you have a time step and you are taking data. From this data, you are basically using an average of what happens in the 15 minutes, in these 15 minutes. And this is a different story because if you make averaging, you give an energy meaning to what you are considering. While if you are doing sampling in the way I told before, you don't care about the reproducing the precise energy that you are using. So in my view, I mean, if you are using averaging, I would avoid the term sampling, or at least I will be a little more clear on that.
Yeah, absolutely. I saw your comments in the report, and I fully agree. It was more like let's say not really precise way of expressing the fact that here we talk about discrete optimization and control problems. So problems that are solved over a discrete amount of samples, or if you want time instance in the problem. But I mean, I will clarify that in the manuscript because, as you said, it might lead to sort of confusions.
Okay, thank you. And I'm not trying to go in let's say more practical on a more practical view. First of all, you have used a real system for your testing and so forth. I don't know whether you can respond to this easily, but what you did is very interesting. Is there any practical perspective to be implemented on the real system, or is it already implemented in some way?
In the real system,
yes.
You mean in the company? Yeah,
In
yeah,
the company, yes.
Yeah, they are actually working on that right now. Not really at the level of distributed optimization, which is a bit too, let's say, too much in the future as for now, but the transition from deterministic to a stochastic approach using this, in particular the stochastic economic MPC, so this combination of scenarios and economic objectives is something that I think from the discussion we had, they are going to implement in the next few years.
I really hope that because you show benefits, and so it would be really interesting to see in practice how much benefit there is on the field. Because I mean the potential, let's say, again, of what you did is very interesting, very important. So it would be a good possibility also for the company. But
hopefully they will get the same results. Otherwise, might look a bit strange.
That's it. Again, on some practical things, you did this partitioning into the energetic period and fluid period, which is reasonable. And if you can go back to slide, I think 47.
Yes. This one?
Yes, that's okay. So just a curiosity. So here there is a sort of threshold set at 1,500 cubic meters per second, which is from the energetic period to the fluid period. It's very clear that in the fluid period you cannot use the storage capacity because there is another objective which has more priority, so is to leave water go. I have just a curiosity. In the first part here of the flood period, we have a first part that is going down and then the other one that is going up. Can you comment a little bit on this?
Yeah, I actually I don't know the specific reason for that, because this is just an example. So in total they have 12 hydropower assets with 12 different operational curves. So this curve will change for each hydropower plant. And the reason why you see a specific shape is because of many reasons. So they model in a, let's say, in a compact way with these operational curves, different constraints. So safety constraints, agricultural constraints, or even internal constraints of the hydropower plant. So how you use the barrage and the hydropower systems within the hydropower plant. So it might depend on several things. For this specific example, I don't know why it has this specific shape, and I'm not even sure that the company is willing to say that or comment on that.
Oh, it's okay. It's okay. I understand that there are constraints on the use of water that depend only on the flow for energy. So there are many agricultural other things. It's okay. It's reasonable. Uh, just thinking about what may happen in a real situation, also connecting to one of the questions you had before, when we have a flood coming, there is some time for going from one place to another. So let's assume that you are using your system in your energetic period, and then you have flood coming from the top. I mean, because of many reasons that may happen. So how can you adapt the situation? Because there is a speed of the flood coming from one place to the next one, and there is also a period for adaptation. What happens with this storage?
So you mean in relation to how much time we need to compute the decisions, and this is adaptation in this sense?
Yes, in this sense.
Yeah. It's the time that we need to solve the dispatch problem in particular with MPC, or even more with the distributed control, is much lower than the time that you need to see the flow. So you won't really have a problem to recompute.
For the computation time, I'm sure that there's no problem. But for the adaptation on the physical system, on the real system, so if you have already decided what to do with the storage, then you have to change your plans. How can you adapt your plans, taking into account that you are in a changing situation, a flood coming on a decision that you have already made for your storage?
This is accounted in within the MPC approach. So the fact that you have a prediction horizon which looks 6 hours in the future will give you not only a hint about the present situation of the inflow, but also on the next, let's say, on the future dynamics of the inflow at each hydropower plant. So you will progressively adapt to this, looking in the future with MPC. That's why also in the real physical system of the company, they are already using model predictive control, just not economic.
Okay, fine. Now, another question which is more general. If you had to start again your PhD now by knowing the result of your study, would you use the same approach?
Wow. Yeah, I would say that one thing that I wanted to investigate, but I didn't have enough time, and I'm planning to do this in the near future, was an alternative to MPC in terms of online control. Why? Because with MPC, you really need to rely on forecast. With online control, you don't need forecast. You just take decisions based on past and current observations. And since one of the main drivers of this thesis was the need for scalability, I think actually that with this kind of approaches you can do better than what we do here. That's why I put them in the perspectives, even though there is a big question about reliability of the method when you go with online control. So But yeah,
Yes.
I would say that if I already had done this work, if I had 1 year more, I would start with something like this.
Okay. Well, a good prospect, indeed. And about if you use different types of couplings, and it's okay, you use spatial coupling and scenario coupling and so forth. Could you say something more about the intertemporal constraints that you have, in the sense that it's okay that the scenarios may be coupled together and also the assets, but when you are using your data for a given period, even in model predictive control, which is the impact of the intertemporal constraints that you may have?
So the temporal in the specific case study of CNR, we have a temporal coupling in the model of the hydropower plants. So there is the reservoir water level at time t will depend on the reservoir water level at the previous time, and this is the temporal coupling that we have. We try to give a generic formulation for that in the manuscript, so that the decoupling which is shown then in the decomposition methods can be generalized to a general aggregation. The reason why we do not account specifically for the coupling of scenarios of the scenario coupling in the decomposition is that you can easily get that with MPC. So with MPC, you can break the problem in time, look only at the specific prediction horizon, and be scalable with respect to the temporal dimension if you want easily. I mean, easily depends on the problem, but I mean, you can do that.
Okay, thank you. I think that other questions were already covered by the discussion you had with my colleagues. So for me, it's okay. Thank you very much, and congratulations for your nice work.
Thank you very much.
Thank you very much, Gianfranco, for the questions. So we proceed now to the fourth person to ask questions. So Professor Malcolm McCulloch from the University of Oxford.
Hi, Franco. I really enjoyed reading through your thesis. That was great. I'm going to start off with a very generic question, which is taking a quote from George Box, who's a famous statistician. He said, "All models are wrong, some are useful." Can you comment on what you believe now, what is wrong with your model, but also what do you believe is the most useful components of that model?
So yes, it's quite true. I mean, of course, I mean the fact that each model has its own limitations. I see different limitations at different levels of what we propose. So as we say, for the MPC, the fact that you have to rely on forecasting its limitations in terms of scalability. Even in the modeling that we give of the uncertainties with scenarios, of course, scenario-based stochastic programming has its own benefits and limits. So the fact that it's specifically tailored for the average, let's say, for accounting for the average behavior of the uncertainty rather than hedging against worst case scenarios. So for that reason, probably going with a robust optimization approach using, for example, an uncertainty set can hedge against very specific worst case situations like these flood periods that we might encounter in the CNR case. But on the other hand, even a robust optimization has its own limits. So the fact that you have to set an uncertainty set, for example, for uncertainty sources which are unbounded, because you cannot really bound the price, for example, in the market or even the inflow in the hydropower plant. So I mean, each one has its own limits. Of course, you can do alternative approaches. There are some things that I think are quite good, and it's difficult to find a better approach. Some others that might be more questionable, but yeah.
Great. Sorry, I was just unmuting. My mouse button was giving me trouble. I just want to explore a little bit more, which others have done on your hydro model. It's about give or take 300 kilometers from Lyon down to the sea, roughly, on the Rhone, because you're looking at the lower half of the Rhone. Is that correct?
Yeah, more or less.
So what's the time scale? How long does water take to get from Lyon to the sea, roughly? I just want to get a feel for the problem.
From the first hydropower plants, it might take a few hours.
From Lyon to the sea, all 200.
Yes.
A few hours to 280 kilometers. It can't be that. No. You can't be going that.
No, from the very top, not from Lyon, from the very top of the hydropower cascade, which starts from Switzerland, actually.
Okay, so from there to the sea, you're saying it's going to take a few hours.
What? Sorry, from where?
Okay.
Not in the lower part, not from Lyon, from the very start of the cascade, which starts from in Switzerland.
Okay, so
we only consider the second part of the cascade for the problems, but the whole set of assets that are considered by CNR, it has also an upper part of the cascade which partially is operated in Switzerland, and then in the French part of the Rhone River.
Okay, so you're saying that it takes, because I'm trying to get a feel for how long water takes to go from one hydro plant to the next one, because they're more or less evenly spaced. Is it about an hour or so, or less than an hour? How long does it take to get from one hydro power station to the next?
I'm not sure they're evenly spaced. Maybe in the first part, just after Lyon, but after that, it's not. I think it's not really the same distance because of the pattern that the flow takes. So. Because I remember I see very different water propagation levels, for example, at the level of the downstream assets compared to the upstream ones. And it also depends on other physical dynamics, so the head of the hydropower plant and the shape of the river. So it's not only about the distance, let's say.
Okay, well, could you give me a range of the times that it might take? Are we talking 10 minutes, an hour, 2 hours, 5 hours?
No, it's a starting length from few minutes to half an hour.
Okay, because I'm just wanted to check that you were saying it's going to take one time step to get from one to the next. Is that a valid assumption?
Yes. I mean, with the dispatch, we take decisions at 10 minutes resolutions, so you can account for that.
Okay, lovely. Okay, and then if you look at the way you set up your optimization problem, you basically had two components in your cost function. One was to do with energy, and the other one was due to imbalance penalties. Is that correct?
Yes, exactly.
Okay, now can you comment on which of those two dominate?
Well, it depends on the market prices, on the forecast. So let's say typically, even though it might really depends on the forecast, the error that you get on the imbalances on the price of imbalances is larger than that on the energy price, accordingly to the, let's say, at least the forecasting that I have. So when you recompute at the dispatch level, these prices, they will have a big impact in the way in which you recompute the actual dispatch of the VPP.
Okay,
but in general, you cannot really say.
Yeah, because could you just then explain on this graph that you had here, you talk about peak price period. Which price are we talking about?
The energy price in the market.
Because it looks to me like your optimizer is optimizing on peak price rather than imbalance.
It's optimizing on peak price. Let's say there is also usually a relation between imbalance prices and the energy price. So when you see a peak price period, at least in this specific setting, you will see also quite relevant imbalances here, at least. Okay, so that's why it is accounted quite explicitly by the controller. Yeah.
All right, because I was kind of surprised to see that in your figure 316, which I don't think is on here, where you actually kept the prices fixed. it was only then that you could see the impact of imbalance coming through. Could you comment on that, please?
Yeah, if you take out the energy price and you assume it's known, for example, at the dispatch level after the clearing of the market, then you will only have a forecast on imbalances, on the price of the imbalances, and this is the main driver of the dispatch. But it's more for the second level of the strategy, not for the scale, not for the bidding approach, for the way in which you recompute the schedule at the second stage.
Okay. I'm now going to go to a bit more of a general question, and then I'll dive into one more deeper. The general question is that you spend quite a lot of time in introduction saying you're looking at a commercial approach rather than a technical approach. So my question is, if you were to stand back, how would you align commercial markets so that it actually meets technical markets in a better way?
Well, let's say we are not really taking them. If the question is in relation to the, let's say, market operator or the way market is structured,
Yes.
I'm not. We are not taking the perspective of a market operator. So it's just an aggregator taking part in the market as a price taker. So you cannot really make the rules on this side. What we assume, even in the simplified case studies that we have in the manuscript, is that the procurement of services is market-based, as it will probably be in the next few years with ancillary services markets. And there are a few small case studies in the manuscript as an extension of this work on how you can optimize in a multi-market trading case, considering ancillary services. But not really on a technical BPP in the sense of a BPP which has no economic objective, but is just used to mitigate congestion or things like that. We don't take that perspective here.
Okay, and then right up front, you make the distinction that the company uses about 80% of its energy in energy contracts and only about 20% for playing these other markets. Was that assumption, did that hold true did you check whether that was still true in the markets that you're playing with? Did you only use 20% for the other markets, or did you dip into the other 20%, or do you use less than 20%?
We were just focusing on the market participation. The 80% that is mentioned there is traded with the future contracts or bilateral contracts with the company to hedge against stochasticity, and we assume that is a starting point. What we want to optimize then is the participation in the market, so not the planning phase, which will decide how much to allocate on the futures and how much in the day-ahead market, for example. So I didn't evaluate that. It's a constraint from the company, let's say.
All right, but you didn't build that into your optimizer to ensure that you still met your 80% that you were contracted to meet?
I don't think that comes from optimization on their side. It's more like an economic knowledge and decision that they have. I don't know the specifics, but it's a fixed quantity that they trade on futures there. So to the best of my knowledge, they say I don't think they use optimization for that planning phase.
Okay, and then my last question is for your training or for your validation data, you used 2017. Quite a lot of studies have shown that you need to at least do a decade because the weather fluctuations happen over longer terms. Can you make any comments on that, please, on the impact that you think it might have on your particular work? Do you think you're robust enough to look at decadal work, or are there some concerns there that you might worry about?
Let's say it's more on the choice of the year was more on an optimistic choice, in the sense that I had also data for the COVID period, in which the market went a bit crazy. So the hope was that that will not happen in the future, and the let's say normal situation will be restored after the COVID period, which, I mean, with similar patterns of the pre-COVID period. In terms of market prices, for example. Of course, if you have very extreme situations, or maybe if you have specific patterns like negative prices, you might also have to adjust a little bit the way in which the bidding problem is computed to keep consistency. Otherwise, you might see some strange things. And it also, if negative prices arises, then it will make sense to introduce another source of control in the VPP, which is curtailment, which we do not consider yet, because we assume we will not observe negative market prices. But
okay, so that's one of the challenges to your robustness, is to say if you've got negative prices, your techniques as they stand don't cope with that well.
That will definitely be something interesting to investigate. Yeah.
Okay. Great, that's me done. Let's move on to the next person, please.
Thank you very much.
Thank you very much, Malcolm. So just now we'll consider questions of Jalal Gazampour from DTU University. Can you hear us, Jalal?
Yeah, I'm here, and I hope you hear me.
Yes,
yeah, perfect.
That's fantastic. Very good job, Luca. Both the thesis, the works you did, and also the presentation today, and also the way so far you responded to all the questions. I really like that. It shows a high level of maturity, scientific maturity. That's really nice. Also, what else I want to say is that your PhD topic is industrial PhD, right? So usually with industrial PhD works, it's expected to have more applied research. While of course also your thesis is very applied, but at the same time it has a lot of mathematical components, which makes it exceptional. So I'm so happy. Well, Luca, you visited me for 4 months, so we had a lot of discussions in that 4 months. So, but still I have to ask the questions. But since I'm the 5th one, most of my questions already kind of overlapped with other questions of the other examiners, especially those of the first examiner, Oscar. He asked most of my questions, but still, I like to get back to those questions. So if the first question is about synergy, so we do coordination. Let's say we have 2 different assets, both belonging to CNR, wind and hydro, sorry, and we would like to coordinate them and bid them together rather than separately bidding to the market. And I suppose this means that there is synergy. Otherwise, we can bid them separately, right? So what is the main reason of synergy? Is it because of reducing imbalances, or is there something more?
So what the results show is that in terms of hedging against the penalties of imbalances, there is really a benefit in using this flexibility potential. So what I can say on that is that if there were very low imbalances, prices of the imbalances, I mean penalties due to the imbalances, you might see situations in which actually the benefit of a coordinated approach is reducing significantly compared to an uncoordinated approach. Then, as I was saying, as we're speaking about weather-dependent units, you might also have smoothing effects, which are not really something that you gain with the controllability. Is more an inherent property of the physical aggregation that you will get. Yeah. Dependently on the specific variability. So okay. It's a bit intricate to distinguish between what is coming from the smoothing and what is coming actually from the increased controllability that you have on the VPP.
These 2 things are connected, right? You're talking about reduced imbalance and better capability of forecasting because of the smoothing effect. But these two are interrelated, right? They are not two different things, or are they?
Yes, exactly. And that's why it's difficult, I mean, to distinguish what's coming directly from the control action that you make, or what's coming from a smoothing effect, which makes easier to forecast what will be the power generation and lowers the error.
Okay, this is a very convincing answer. I fully agree. But the thing is that most European countries now they move to one price scheme. Maybe France is still using two price, I guess. But at least in Nordics, it's now one price. I think all EU countries are moving to one.
Yeah, there is. Yeah.
Do you know what scheme exists in France? Is it one price or two price?
It's dual pricing scheme, but as you said, they are transitioning to one pricing scheme, and it's all the whole Europe. So,
well, this is not part of your thesis, but let me challenge you. If say that from tomorrow, French TS switch it to one price, is all coordination benefits you just said, are they gonna disappear?
but still you will have a price for the penalty, so you will have to hedge against the error with respect.
Not only for penalty, also for reward. So now with imbalance, you may gain under one price.
Yes, but I mean, you mean you will gain to be in an imbalanced positions rather than keeping the
it's one price
promise.
Scheme, right?
Yeah,
exactly. Gambling. You may earn, you may lose, depending whether you forecast correctly the system imbalance and create imbalance that helps the system or not. So it's fully a gambling. So you may have motivations to create imbalance. Am I right?
But, yes, I agree on that. But still, you might exploit this flexibility to play, let's say, in a strategic behavior like this if you want. So even to be an imbalanced position, especially exploiting the intratemporal constraints within the market. So the fact that you might have an energy price at a given level at time t and an imbalance price which is higher at time t plus 1 or lower with respect to the previous instant of time. So playing on the intratemporal constraints.
Okay. So you hypothesize, of course, this is not part of your thesis, under one price scheme, there might be still some good reasons to do coordination.
I think the underlying message is that we can exploit flexibility to enhance the controllability on stochastic units. So independently on, I mean, not completely independently, of course, but if there is still a benefit in having flexibility, so in shifting and modifying the power generation or consumption that we have, independently on the price scheme, if there is this benefit, then it might be beneficial to go with a coordinated approach, in my view.
So let me move to the next question. By the way, do we assume that all assets belong to CNR? It doesn't mean that there are two, they have different owners, just CNR do the coordination for them, or is it the case?
The hydropower assets are a whole property of CNR, but there are third-party units in among the wind and solar power plants.
Okay,
which they
so
operate.
Now that makes my question maybe a bit more relevant, since there are different ownerships. Don't you think that for your coordination method, we need to add extra constraint enforcing individual rationality, saying that I will participate in this coordination only if the profit I gain is not less than what I can gain individually?
In a general case, that's absolutely true. And there is also other questions, how, for example, to allocate the profit among the resources integrated.
Yeah, it's the next question, but actually this is the first one, saying that, okay, if you tell me that, Jalal, you are part of this and you will gain less than what you could earn alone.
Yeah, it doesn't make sense.
I believe, sorry.
Yeah. Well, what I know from the company is that they have like a fixed contract with these owners, so they will pay them only when they use their capacity and at a fixed price, plus some rewards that they get from the French government from the integration of renewables. So it's everything is fixed. But in a general case, yeah, of course, it will be something to optimize in addition to the energy management. Yeah.
And then I fully agree that then this profit allocation is a second complexity on top. But it's not just also profit distribution, also risk distribution, right? Since that you have scenarios, you have to make sure that there's a fair allocation of risk among people.
Yeah, introducing a measure of the risk that you will incur is something that
No, I'm not talking about risk introduction. I'm talking about sharing risk among two different owners.
How to share it among different owners. Yeah, exactly. Even it can play a role as much as how we allocate the profit, of course.
Okay, let me move on to the next question, Luca. So you assume the whole portfolio is price taker, which is fair, but I suppose now the French TSO, like other European TSOs, they maybe not TSOs, sorry, the EPEX, the market operator, they share afterwards the aggregate curves of suppliers and demand. So we know that after market clearing a day after, where our bid located. So have you checked ex post whether the assets, the whole portfolio is really price taker or not? It might be price maker. Because you know where you bid, you see your position, your bid in the supply curve, it's the public information. And then you can see that by changing your price, whether you had a chance to impact the market prices or not.
Yeah, that's very interesting actually. Again, as here we are only operating renewable energy sources, and the share of renewables in the French market is very low. I don't think that you can actually see in a general situation a player like CNR which becomes a price maker in the French market because of the large penetration of nuclear power that we have here. But again, in a general case, that can be.
But do you know that EPEX publishes those information publicly?
I haven't, but I haven't made specific simulations on that. So I'm speaking about only my intuitions, not really results that I have.
I see. Let's talk a bit about the work you did at DTU. So this ADMM things with guarantee, performance guarantee. Can you remind me what kind of guarantee we have?
So the performance guarantee that we have is the reliability that we get through these bounds. So the fact that we enforce upper and lower bounds is, first of all, we get a measure of the optimality. So at each iteration of the ADMM method, we can evaluate the distance between these two bounds and compute an optimality gap. And then through the proof that we work on together on DTU, we are able to show the existence and validity of these two bounds. So we will always be able to compute a new value of the bound and use it to enforce this performance guarantee.
So when your ADMM algorithm converges, does it mean that the upper and lower bounds, they reach together or not? It's still, this bounds might be different than the point we converge.
The point at which you will converge is it's decided by a parameter and a sort of gap threshold that is set by the operator. When the optimality gap, let's say like for branch and bound in MILP solvers, is below the given threshold given by the operator, then you will assume that the algorithm has converged. How you set this parameter is also something interesting that we haven't looked into very much actually.
What I'm trying to, get is that is it a chance that we converge with a given optimality gap of branch and bound, whatever it is, but still we converge to a local optima, and we are far away from those upper and lower bounds, optimality bound. Would it be the case?
No. We cannot converge to.
so
the
say that
distance
it's 1%, it's a small value of, I don't know, milk gap.
No, then if it is a small value, then I mean the gap, it gives you the distance from the optimum value, so it will be at most the value of the gap. So if the gap is the threshold is 1%, the error with respect to the global optimum will be at most 1%.
So it's good and nice to hear that. And can you remind me why we eventually decided to use progressive hedging or consensus ADMM or whatever? Why not other scalability methods?
This is something, I mean, one of the things that, as I mentioned before, can be, I mean, adapted. The idea for me is that consensus ADMM and specifically, I mean, progressive aging, if you go with scenarios, is quite an adaptive method. So there are methods which for me are very tailored to the specific set of coupling constraints that you decouple, like benders, which usually is used for two-stage stochastic problems. I see really the potential in consensus ADMM to build a simple structure through these consensus constraints that can be that can enable a reformulation of the problem for full scalability and the application of these ADMM methods in a very straightforward way, while decomposing in multiple directions. So with respect to scenario coupling, electrical coupling, so it's really the flexibility of the method which has driven this choice.
Do you have also any other methods that could be applied to this, your problem? Your problem is mixed integer nonlinear eventually, right?
Yeah.
And so can you think of any other method that could be an alternative?
Still, I mean, distributed methods or?
Yeah, any kind of composition or distributed method.
I mean, you can, in terms of distributed methods, you can go with more generic formulations, like using more like proximal methods rather than a specific ADMM, which is also a proximal method, but you can go with a more generic formulation of a proximal method. As I was mentioning, I really think that online approaches can be very beneficial. Because they make a step forward with respect to MPC in decomposing with respect to the temporal constraints, but they can also be combined with distributed methods to get the decomposition with respect to the other coupling constraints. And there is a paper about that, I think, which is very nice. So, I mean,
Okay,
there are alternative
I
methods.
suppose you couldn't implement benders because you have binaries in subproblem. But maybe you could also think of dancing wolf, for example. I know there are papers.
That's it. That is also an option. It's the whole thing is to find the, let's say, something that blends both scalability and reliability. So, and on the other hand, I really like, as I say, this consensus ADMM idea because of its flexibility that offers. It's not really specific to the problem. But of course,
you
you
don't
might
have problems with this parameter tuning, or did you?
This is the main drawback for this kind of methods, I would say. The fact that depending on the tuning of the parameters, all augmented Lagrangian relaxation-based methods that I've seen, they really depend on how you tune the parameters.
Good. So look, I have one last question, and it's a bit pragmatic question. So you did all this consensus ADMM and all these things, but for CNR, I think they paid your PhD, if I'm not wrong, for part of that. But did they find your method pragmatic in the real world, or do they prefer, you think, I don't know, maybe easier solutions, maybe something based on decision rules, or I don't know, some linear policies? What was the takeaway there?
You already answered this question when I came at DTU, actually, because the first time I remember we met and you suggested this idea of the bounds. You told me that it might be very beneficial because the industry, they really like these simple ideas that they can fully understand in terms of bounds. And it is actually what was the feedback from CNR. So even though maybe it is not interesting at this stage to go in the specific of how we solve the method, the general idea of enforcing reliability through upper and lower bounds is something that they really appreciate and fully understand in terms of value for their case study, even though they will not implement this tomorrow probably, but still is something that
Very good, Luca. Thanks a lot. I enjoyed talking to you. And
Thank you very much.
Congratulations again for nice work.
Thanks.
So thank you, Jael. So now it's my turn. So first, I would like to congratulate you for the quality of the work you produced during your PhD thesis and
Thanks.
also the clarity of the presentation. And finally, I would like to thank the advisors for the invitation to be part of the jury for this really interesting PhD thesis. So I am the last one to ask questions. So just I had a list of questions, but most of them were covered previously by mainly the question about the bidding curves, and just if you introduce other type of bidding curves, you can introduce more smoothness also in the process. Also about the fact that the assets may belong to different stakeholders, which is really an important topic. So I'll still ask you some questions. Just so that we are talking about a market. And so what's the typical size of the market you are considering for your problem?
The in terms of liquidity, you mean, or like the market?
The number of agents, whatever, because you're in your bidding process.
We consider, I mean, from the market point of view, it's simulations based on data from the real day-ahead French market. In terms of participation on our side, the assets are say a combination of hydropower plants, wind, and the storage. The capacity, I mean, the impact that you will have in the market, as I was discussing before, I don't think it enables you to play as a strategic behavior.
But what's the number of agents in the market? Markets you were considering more generally, because you would like to define a general process, okay, general model, okay, what this type of problem. So as a general way, what's the size of the market you would consider? Do you have an idea about that, or just
we do not make explicit assumptions on the size of the market, as we assume that we will bid in the market and we will get paid as bids. And so it doesn't really play a role in the way we model it, the size of the number of players involved. Then, of course, dependingly on the specific real world market that you will consider, you might have different situations. For example, you can play strategically or not on, but we do not make assumptions on that.
Okay. So if we consider the virtual power plant, so just again, so the questions about the stakeholders taking part to the virtual power plant, but just if you consider a particular use case, but as a general rule, so for your approach to be quite efficient, okay, just what is a good balance about the different assets you would like to consider into your virtual power plant? So just because you have a different type of flexibility. So here it was hydropower, but you could consider other type of flexibility, as you mentioned during your PhD thesis. So just in order that the virtual power plant be efficient, you need to have some balance between the assets in some points, or just do you have an idea of just what could be a good balance for?
Yes, it's something that we try to evaluate in some of the simulations that we considered. So, for example, when you see here this figure, we were trying to evaluate how much wind capacity we can integrate before consuming the total flexibility of the hydropower plant. And you see that this will converge when the wind power capacity is above like 14 times the hydropower capacity of the cascade. So you can get, let's say, a wind capacity which is 40 times higher than the hydropower plant capacity, the hydro capacity in the VPP, while still observing a benefit compared to uncoordinated approaches. But this is very specific for the plants that we consider in the case study of CNR. It might depend on other things. The geographical placement of these assets, for example, will play a role. Here we just increase the capacity with a multiplier. We do not really consider it as parts portfolio.
Yeah, of course, but it's quite a general question. Because, of course,
it's not easy to evaluate the balance. Also because you might also put inside the VPP and aggregate additional flexibility sources like energy storage systems and exploit them together with hydro to get flexibility. And that will be interesting to see how they coordinate.
Yeah. For example, for an aggregator who is looking for different stakeholders, just to have an idea about the dispersion of these assets could be quite interesting. But just it wasn't the topic of your PhD thesis, but just
absolutely it's quite interesting. Yes.
Also, I had a question about your objective function in your day-ahead market, because sometimes you are talking about profit, you are talking about revenue, you are talking about cost. Just sometimes there are confusion because revenue is the profit.
If I say the revenue, it was a mistake. It's just profit here. We do not assume any cost of operating the hydropower plant, so it's profit. If I say the revenue at some point, it was not accurate. It's profit. Where you see cost here is just because the profit, you see, like in the green objective function, the profit is modeled with the minus sign because it's a minimization. We want to minimize this objective function, so it takes the meaning of a cost, but it's still the reverse of the profit.
Okay, but so also it's also depending on your case study, but if you could have different type of assets for which you could have also some cost, operating costs with fixed costs and so on. So do you have an idea if you could integrate that into your approach, or what the complexity could add if you have fixed cost for some assets and so on? So
let's say in the manuscript, we provide a generic formulation of the objective where in addition to this term for the energy price and the imbalances, we also have operational costs, for example, for the storage systems. This will not impact too much, I think, the centralized approaches or what we propose for the first part. But when we go to the distributed approaches, depending on the nature of these cost terms, if they are convex or non-convex, it will play a role. For example, storage degradation usually is evaluated with a non-convex function. And this will impact, of course, the way in which we decompose the problem. So it might have an impact specifically for the second part, for the methods presented in the second part, the distributed methods.
Okay. Also, another general question. So you are, of course, you are optimizing in an uncertain environment, and you consider scenarios. But do you think it could be interesting to consider risk-averse options with conditional value of risk or whatever, just because you can have different value of risk for the stakeholders?
Two things on that. One is that we haven't really simulated what happens if you put inside a CVAR measure in the problem, but still this will account for the probabilistic behavior, in my view, of the problem, at least, and of the probabilistic model of the uncertainty. So the average behavior that you see with these scenarios, it will edge against the average worst case, if you want. What I see as a real alternative to edge against risk is a robust optimization, and to set an uncertainty set and see how this will play with respect to hedging against very, very worst case scenarios like heavy float periods for a lot of consecutive time steps.
It's not really equivalent because in robust you are in the worst case, but we can have different value of different risk measure, but just it's another option.
No, it's clear that it's not equivalent. What I'm saying is that a real alternative to this is I see it more beneficial or robust optimization than including a CVAR measure. Then of course it's not the same thing.
Okay, great. So maybe two other questions. You are talking about that you need only 20 scenarios. Okay, but in fact, the scenarios should be quite heterogeneous. So do you have a measure about, do you have other measure about the disparities of the scenarios? So because if you take 20 scenarios quite similar, you have not the same value. So do you have an idea about that?
That is also linked to what I was saying about the characterization of the uncertainty. So the underlying assumption here is that with these three key sources of uncertainty, so wind and solar, inflow and prices, they are assumed to have a low correlation. So we can randomly pick scenarios and combine them because of this. And this is a result of the company. The number of scenarios that we select, say, given the fact that you pick from the set of original set of scenarios, these scenarios randomly, and you combine them with the out-of-sample validation, we show that with the 20 scenarios, we can accurately represent the uncertainty. But if we were using a more smart way of reducing the scenarios, for example, smart scenario reduction methods, you might get another sample validation which gives you a lower number of scenarios required to represent the uncertainty, because we can pick just 1, 2, 3, 4 scenarios that accurately represent them in a given period. So it will depend not only on the number, but also on how you select these scenarios, of course.
Yeah,
here is just a random sampling from the scenarios.
Yeah, it's related to your use case, but in a general rule, you need to pay attention also to the heterogeneity of the scenarios you consider.
It will depend on the spatial temporal correlation that you have among the uncertainty, but it is not really the topic here how to make forecasts, and that is more how we use that to make decisions.
Okay, so I had also questions about decomposition approach, but they were already covered. So just in your manuscript, and you also mentioned it in the answers to the questions, you mentioned that you need to pay attention to the tuning of the parameters.
Yeah.
So do you have idea about how could use some learning approaches to tune the parameters? So what are the parameters that are the most important? Is it about the regularization term?
Yeah, it's not something that, let's say, I came up with. It's something that is largely studied in the area of augmented Lagrangian relaxation method. So basically, you see here is a sketch of the algorithm. We have two main parameters, which is sigma, which is employed to update the penalty parameter rho of the algorithm. And then we have a parameter epsilon, which gives the threshold. So when we go below this value, the algorithm has converged. Now, if one has more impact on the other, I think you cannot really say based on, as a general rule, it will depend on the problem because of the specific way the primal and dual variables update are formulated. But there exist adaptive ways to smartly update these parameters, as shown, for example, in a famous paper from Boyd, which is cited here at the bottom part. In the bottom part of the slide, the adaptive way for updating sigma based on these residuals. So then based on a specific measurement that you make during the algorithm at each iteration is very effective and comes from this paper. But it's, I mean, an heuristic method. You're not guaranteed to be optimal. It's just, yeah, something that typically works in a general case.
Okay, and my last question is about the last chapter of your PhD thesis when you consider a multi-market approach and you decided to just to consider a summation of the two objective functions in the two markets. The budget,
Yep.
is it why is it chose? Because it's in fact you assume that the two markets have the same importance, but is it the case, or why
Well,
not
again,
to use weighted functions? It's an open question. I don't know. I have no idea. But
within the objective function, the weights will be given by the prices. So it's let's say inherent in the formulation of the objective function, because I mean, if you have no additional constraints, what will drive your decisions is only the prices that you will see in the market. So if it is more beneficial to participate fully in the ancillary services or in the day ahead or mix them, it will be decided by the prices. I don't know if you might include additional, weighting constraints, maybe to hedge against risk, for example, or stuff like that. But yeah, it's not a specific formulation that we consider in the case study.
yeah, of course. Also, it was the last chapter of your PhD thesis. But
Yeah, it was just insights
that,
on how to expand this to the multi-market trading case.
Okay, so thank you. So I have finished with the questions. So
thank you very much.
No, I will ask the supervisor if they want to ask questions or make comments. So just.
Yes, Luca. So no questions, just maybe a feedback on the experience working with you. Actually, it has started by an internship.
Yeah, I was just a master student, still a master student when I came here.
It started from an internship, but really early on, you showed your capabilities of being organized, being curious, wanting to know. Having this balance that also Jalal mentioned between applicability to industrial problems, but also more theoretical insights. And so we see that this journey has continued. And so I just want to wish you the best for what comes next, because as far as I know, you will continue your academic journey now.
Yeah, I will.
On a related topic. So you may discuss that further with the other members of the jury. So again, thank you for the collaboration, and it will continue, I'm sure, with some publications.
Thanks for your mentorship over these years.
Yeah, from my side, I would like to share the comments of Simon. The collaboration was very nice and smooth, and we admired actually that you are hard worker. So this is somehow reflected also on the dissemination efforts. And I don't want to take much time, but I would like to profit to thank our industrial partner, actually CNR, who support this PhD and gave us the flexibility also to explore areas which would be more in the frame of an, let's say, a pure academic PhD, despite the fact that we don't have in France separation between industrial or academic PhD. Our objective is always to have some theoretical contributions at the level that's possible. And of course, to thank Jalal for hosting you for a few months at DTU. This has been a nice collaboration, and I pass the floor to.
I think I forget something. If people in the audience with the PhD thesis want to ask questions, they are free. I just forgot. Okay, so no more questions. I think you had already a lot of questions. So thank you again.
Thank you very much. Thank you very much for attending, and for the questions and for taking the time to review my work and make questions. So I really appreciate it. Thank you very much.
So just we go out for deliberation and we come back in a few minutes.
Okay, thanks.
So I think that you have another link for the connection. So we just leave and go back in the office and in a few minutes. Okay, thank you.
Okay, English and Italic. So the main dish is salmon. It's a salmon or beef palerone. It's a slow cooked beef or chicken curry with coconut. Or no, cheese is more vegetarian. And that sorry.
No, it was 15 of you want to like this? Yeah, let's